Use the first of this year's seminar, Mary Vaughan from Texas State University. Mary will talk about asymptotic expansion of a non-local phase transition energy. Thank you.
Okay, thank you, Stefania, for the introduction, the invitation to speak at this seminar, and everyone for coming today. So what I'm going to talk about is some some joint work with Serena Di Piero and Enrico Valdenoci, who are at the University of Western Australia, which is where I was working with them for the last 2 years before moving back to Texas. And it's also joint with Stefania Patrizzi, who you all know is at UT Austin. Okay, so the main object of this talk is a non-local phase transition energy, but to provide a little context and motivation, let's see. Okay, good. I'm going to first talk about the classical case. So, um, the Ginzburg-Landau functional is a classical model for a two-phase liquid of density U in a bounded domain for the separation between the two phases. So, in the model, you have a potential energy. So for us, W is a C2 double well potential, drawn here in my nice hand-drawn picture, that has wells at -1 and 1. So that's where the derivative is 0. And then between the wells, it's strictly positive. So this -1 and 1 represent the two phases of your liquid. And that potential energy, of course,
Mary, excuse me, we don't see the slides. Are you like,
okay.
we just see the first page.
Okay, let
I
me
know
try
the screen
sharing
is
again.
frozen.
Sure.
Oh, okay.
Can you
Okay.
see now?
Yes, thank you.
Okay, good. Thank you for saying something. Um, I mean, if it happens again, please interrupt. It's hard to watch the chat while, speaking. So interrupt if there's questions or problems. Okay, so I'll just say again, we have our energy. We have a potential energy, which is this double well potential with wells at -1 and 1. So it favors being close to -1 and 1, and that's balanced by a kinetic energy. In the classical model, it's the gradient squared. Um, and so this favors smoothness, wants to minimize oscillation. So you have this balance and you have this parameter epsilon um, in front of the kinetic energy. And so typically up to dividing by epsilon, which I'm emphasizing that for something that will happen a little bit later. But minimizers typically separate into these two regions, a region where U is close to one phase -1, and a region where U is close to the other phase +1. And that region is separated by a small, another region of size epsilon. And so as epsilon goes to 0, this region shrinks, and you have the set where U is approximately equal to 0 is the free boundary separating these two regions. And famously, Modica Mortala, they showed that as epsilon goes to 0, that energy divided by epsilon, gamma converges to the perimeter of the set where U is equal to 1 in omega. And gamma convergence is the type of convergence I'm going to be talking about for the entire talk. So I assume that probably everyone here knows what gamma convergence is, but just I don't know, in case there's some graduate students that don't know, I just want to have a quick one slide. This is what gamma convergence is, so that when I use the terminology, we're all on the same page. So we say a sequence of functionals defined on some function space X, gamma converges to another functional as epsilon goes to 0 if the following happens along subsequences as epsilon j converges to 0, as j goes to infinity. So the two things we need are first, for any sequence uj that converges to another function u in your space, then the lim inf of your functional evaluated along that sequence is bigger than or equal to f of u, f being the limiting functional, and the limiting function u here. On the other hand, we also need that given any u, we can find a sequence that converges to u so that the lim sup along the sequence converges to the functional evaluated at u. So in particularly for that recovery sequence, we call it from the lim sup inequality, you have equality for the limit. And when all of this happens, we'll write f as the gamma limit of f epsilon. And one of the powerful consequences you typically get from gamma convergence is that sequences of minimizers of f epsilon. So if you have a sequence of minimizers that converge, then they converge to minimizers of your limiting functional f. So that's part of the power of this gamma convergence setting. So that's the type of convergence that Monica Mortala considered. Now, what we're interested in and what we'll be focusing on for most of the talk is a non-local phase transition energy. So in particular, we're looking at the fractional Allen-Kahn energy, where we have the same potential energy. So this is that double well potential with wells at -1 and 1 that's now balanced by a non-local kinetic energy. So it's non-local because we have this double integral that sees values of u at x and y for all x and y, where at least one of those pairs, x or y, is in omega. So this domain of integration here neglects when both particles are in omega complement. So just for a moment, I'm going to go to the next slide just because I drew it for those that don't come from the non-local world. That we're in that domain of integration for the kinetic energy. Either x and y are both in your domain omega, or at least one of them is. So we neglect when both of them are in the complement, because when we work with non-local, the complement of your domain are your boundary conditions. So we think about everything in omega complement as being fixed, and we will actually incorporate that later in the talk. Okay, so that's the kinetic energy, and we call it fractional because we have this parameter s here that ranges from 0 to 1. And as s goes to 1, this energy converges to the classical Ginzburg-Landau energy functional. And you see that in the coefficients as well. So for the coefficients, the scaling with epsilon, it depends on the value of s. So you have this critical value s equals 1/2, where the scaling changes when you're below 1/2 or above 1/2, both in how you scale the kinetic energy and the potential energy. And this is the correct scaling. It was considered by Savin and Baldinocci in a couple papers. In particular, I want to talk about the excuse me, the 2012 paper, because that's where they proved the gamma convergence, which, as I said, is the I guess I would say is the non-local counterpart to the Monica Mortala result that we saw. So with this different scaling, that s equals 1/2 is a critical value with the gamma convergence. So they prove when s is bigger than or equal to 1/2, the non-local energy, when you again divide by epsilon, converges to the classical perimeter functional. So you have this non-local energy that localizes in the limit. So here u and omega is equal to 1 in the set E and -1 in the complement. So this is again the perimeter of the set where u is equal to 1. And up to this constant here that depends on dimension s and the potential. On the other hand, when s is strictly less than 1/2, the long-range interactions play a bigger role. And what they show is that the energy, again, divided by epsilon gamma, converges to a non-local energy functional. So you don't localize in this case, you are genuinely non-local is the terminology we like to use. And that is still, though, only you have that convergence when u is equal to 1 in some set and -1 in another. And this is the morally, this is equal to the non-local perimeter functional that was introduced by Caffarelli, Rakoshavra, and Savin in 2010. So again, when s is bigger than or equal to 1/2, you converge to the classical perimeter, and when s is strictly less than 1/2, you gamma converge to the non-local perimeter of the set where U is equal to 1. Now, what we want to do is a higher order asymptotic development in the sense of gamma convergence for this non-local energy functional that and Savin and Baldacci considered. So we use the notion of asymptotic development. It was introduced by Ancelotti and Baldo. And what they do, or what the setting addresses, is two objectives simultaneously. So the first one is kind of what asymptotic development, what you might expect from the name, is you want to understand and establish a higher order expansion of your energy. So you want to be able to write in some context with regard to gamma convergence, this expansion in terms of energy functional. So here, you expect that the energy gamma converges to F0, and then up to dividing by epsilon converges to F1, divided by epsilon squared converges to F2. We're going to have some sense of this expansion. And we want to do this in a way so that when I take limits of minimizers that converge to my epsilon energy functional, then not only are they minimizers, are the limits of those those sequences, they're not just minimizers of your F0, they're minimizers of F1, F2, all the way up to whatever order of gamma convergence you have. So it provides a refined selection criteria for minimizers. It gives you more information about the objects that you're studying and their limiting behavior. The other piece of this story, the other objective that comes with asymptotic development, is understanding what happens at the boundary. And this is a big part of what we have been looking at, because Savin and Baldacci's result for the non-local, and also Modica Mortola's for the classical problem, is an interior result, in that they don't say anything about what happens at the boundary. And some of the arguments happen in compact subsets of the domain. So they are interior, and we want to understand, if I fix boundary conditions, what can I say about the limiting functional? So that's what we're going to do. I'm going to introduce the notion of asymptotic development, starting in our setting, but it's a general format. So for us, our function space will be the set of functions, measurable functions, real valued. When you restrict them to omega, they will be in L1 of omega. And I'm going to endow X and all of its subspaces, which with the metric of L1 of omega. So we're neglecting, when we talk about two functions, a sequence of functions converging, we're neglecting what happens in the complement. But for us, that will be fixed. So no problems there. And then to fix our boundary data, we're going to let G go from Rn to -1, 1, be a given Lipschitz function. And to incorporate our boundary data, we define xg to be the class of functions in our ambient space X that are G in the complement of omega. So as I was saying earlier, we have this non-local problem where particles in the domain interact with everything in the complement. So for when I fix my boundary conditions, I need to fix them for in the entire complement of my domain. And now the way we incorporate the boundary conditions is just by redefining our functional. I'll now, for the rest of the talk, just refer to F epsilon being our energy if you have the boundary conditions, and plus infinity otherwise. So that's just how we incorporate the boundary conditions into the functional itself. Now, what does this asymptotic development then within that function space, and for our function with the boundary conditions, what does that mean? I already had this on the previous slide, but this is the notation we use for asymptotic development, and it corresponds to the following conditions. The first one I already said out loud, but what we have is that F epsilon, our energy, gamma converges to F0. So if you don't have that, you can't do any other higher order asymptotics. So suppose you have that. And for the next one, I'm just going to trivially call F epsilon 0 F epsilon. And that convergence happens in X or in XG. Now, to talk about the higher order asymptotics, we look at difference quotients. So if I want to find what, say, the first order term is, I define F epsilon 1 to be F epsilon 0, which in that case is just F epsilon, and I subtract off the minimum value of, um, of F0. So I take F epsilon 0 minus the minimum of F0 and divide by epsilon to give me F epsilon 1. And then I look at the gamma convergence of that new functional and that if that gamma converges, that gives me the first order term in my asymptotic development. And then you proceed in the same way. You take F epsilon 1 minus the minimum of F1, divide by epsilon. So that's how we make sense of these difference quotients. And it's enough to look at this gamma convergence in the class of functions where the minimum is attained, because outside of that, you trivially have that um, um, you can reduce down to this case, I should say. So this is the setting that we want to understand for our non-local problem. Oh, I forgot to say, a nice and you do get from this construction that set inclusion of minimizers that I had on the objective slide, and you also get an asymptotic expansion of the minimum values. So you can write the minimum of F epsilon over um, your function space X in this expansion of the minimum value of F0 plus epsilon, minimum value of F1, etc., plus some lower order term. So then again, that's the part of the power of this asymptotic development is the expansion of minimizers as well. Okay, so as I said, we want to do this for our non-local problem, but just to give a very brief, non-exhaustive some context on what's been done before for asymptotic development. I mentioned that this was introduced by Anzalotti and Baldo in 1993. And they have a couple examples in there, but the main one that they consider is the second order development of a Ginzburg-Landau functional, where they have a double well potential, and but the wells are flat. So you have the well and then two flat parts, say two intervals of positive measure are your wells. And they look at it there. Anzalotti, Baldo, and that was in 1D, by the way. And Orlandi, they looked at the second order development of a Cahn-Hilliard function of the Cahn-Hilliard functional, where you have a single well potential. So there you have one phase, so you don't see the phase separation. But so really it's a study of what happens on the boundary. And they have for the first order term an integral of your boundary condition. And the second order term, they are able to look at that and they have an integral of the boundary data G with a curvature term in there as well. So when you start getting to higher order, you might expect curvature terms to appear. A bit more recently, Dalmaso, Fonseca, and Leone looked at the Cahn-Hilliard functional in higher dimensions and looked at the second order development. And they had a double well potential, and they fixed the boundary data to be 1 on the boundary of omega. And the nice thing there is you know a lot about the structure of minimizers, and they proved that the second order asymptotic term, the F2, was equal to 0. And then Leone and Murray looked at a similar also looked at the second order development of the Cahn-Hilliard with a double well potential, slightly different assumptions. They don't assume that U is equal to 1 on the boundary. And so what they get for their second order term, so if you think for the first order term, you have the perimeter functional, and the second order term, they have a little bit more complicated term, but it has to do again with the curvature of the minimizers. So that's what they see in the second order term. And yeah, so that's just a little bit of context. And we want to do asymptotic development, as I said, for our non-local problems. So just as a reminder, this is the non-local energy we're looking at when you're in XG. F epsilon is exactly this. And we see this different scaling for the potential and the kinetic energies. So we started with the 0th order term, and if you just look at the coefficients, A epsilon converges to 0 as epsilon goes to 0, and B epsilon converges to 0 if S is less than or equal to a half, and it's just equal to 1 if S is bigger than a half. So what you expect is just the potential to survive in the case when S is bigger than a half, and that's exactly what we show. So the 0th order gamma convergence, our functional converges to the potential energy if S is strictly bigger than a half, and just 0 if S is less than or equal to a half. So we prove this explicitly, and the minimum overall X really here of this energy is equal to 0, because in the case S bigger than a half, you can take any U that's G, any U that's plus or minus 1 in omega, and you get 0. Okay. So that leads us then to the first order case. And this we split into two different cases, which isn't surprising thinking about the interior result of Savin and Aldinochi. So we split into the case S strictly less than a half and S bigger than or equal to a half. And what do? We take our functional, subtract off the minimum of F0, which is just 0, and divide by epsilon. All right, so I'm going to start by talking about the genuinely non-local regime. So this is the case where S is strictly less than a half. We'll let omega be a subset of Rn for n bigger than or equal to 1 be a bounded Lipschitz domain. Of course, if n equals 1, you're instead talking about an interval, but we can include it here. And what do we prove? We prove we prove a couple of things, but first we prove the first order asymptotic development. So we can write this first order expansion. We already talked about the 0th term, and the first order term, I would say it's exactly what we expect. So we get the same energy functional, the non-local perimeter functional that Savin and Baldinocci had in this case in their paper. We just have the restriction that U is equal to G in omega complement. So this is the genuinely non-local case because not only do we converge, we have a non-local functional converging to a non-local perimeter functional, but our boundary data is also non-local. Here, we're still looking at U equals G everywhere in omega complement, and I guess a little bit of a spoiler, when S is bigger than or equal to half, we'll see something a little bit different. We'll see localizing with the boundary conditions as well. So this is the genuinely non-local regime. You get the asymptotic expansion of minimizers of the minimum values as well. And the proof is exactly the same as what Savin and Baldinocci did in the interior. So it's not, yeah, it's exactly what they did. But then we asked the question of what happens with a higher order asymptotic development. So that was first order. Can we say something about a second order asymptotic development? So just notationally, remember M1 is the minimum of F1. So it's the minimum value of this. It's the minimum of the non-local perimeter functional here. And if that value is equal to 0, then you have a full asymptotic expansion. I would call it the trivial case. You get that all the higher order terms are 0 if you're a minimizer of F1 and plus infinity otherwise. So more interestingly, we consider now the case where the minimum value is non-zero. What we were able to show was that if you take a minimizer of F1, we can find a sequence that converges in my space, so it has the boundary conditions. G converges to U bar as epsilon goes to 0. But the second order epsilon functional along the sequence epsilon, and this is, you can do this along subsequence as well, just notationally writing it this way, equals minus infinity. So what is that telling you? That's telling you that the second order term in your asymptotic development is minus infinity if you're a minimizer and plus infinity otherwise. So really, there is no meaningful second order asymptotic development at all for this non-local functional. And in fact, more than that, we found a threshold where where you can't have a, say, fractional asymptotic development from some fractional level. So we showed that if you take f epsilon 1 of this function v epsilon minus the minimum value, and instead of dividing by epsilon, which is what you do to get this f epsilon 2, you divide by epsilon to the mu for any mu bigger than 1 minus 2s. And remember, we're in the case s between, excuse me, between 0 and 1/2. And then this converges to minus infinity. So there is no asymptotic development of order 2 minus 2s in the non-local setting. We expect this to be sharp, that there is when mu is equal to 1 minus 2s, we expect to maybe get a gamma convergence result there. So then that would tell you you have this kind of fractional asymptotic development, I guess, or I don't know the correct phrase you might use there. But we haven't been able to prove that. We were able to show there is this threshold. We don't know that that threshold is sharp, but our proof kind of suggests that it might be. And we found this result a little bit surprising. So I thought I would just take a couple of slides and give you an idea on why this is true. So suppose we have a minimizer. What does that mean? That means when I plug it into F1, I get the minimum value. And just as a reminder, this is what that functional looks like. And let's look at the case when the minimizer has a jump discontinuity in the interior. We can also consider when there's a jump at the boundary. The proof is very similar, so we'll just say jump discontinuity in the interior. Then we prove that U bar is an almost minimizer of the fractional perimeter functional in compact subsets of omega. So it's not a minimizer of the fractional perimeter functional. A big reason for that is because we have this boundary data G, which is just a Lipschitz function. So we have to work with almost minimizers instead. But that was studied by a couple people. Valdenoci, Di Piero, and their student Ricardo Vivas, spiking on his last name. They looked at regularity of almost minimizers, and so the point is we have regularity of the free boundary of the set where U bar is equal to 1, and we're able to use that. And so what we do is we localize around the jump discontinuity. So say this is a ball, and over here is a set where U is equal to -1. Over here is a set where U is equal to 1, and this ball is, say, contained in your set omega. So I'm in the interior. Then by the clean ball condition, and I'm not going to get into all the details, but for experts, this might mean something to you. By the clean ball condition, we are able to put a smaller ball for any delta. I can put a small ball on in the set where U is equal to -1, and a small ball in the set where U is equal to +1 of universal radius C delta. C is universal, delta is small, and where the center of those two balls is less than delta. So they're close to the free boundary, but these two balls are contained, you know, in the two separate halves of your contained in the two separate phases. Then what we do is I'll have it on the next slide, but just to reference it on this slide with the picture. In this ball here, in the set where u is equal to -1, I'm going to lift my function up just a little bit. And by doing that, I can show that this energy, that if I take this function u bar and lift it a little bit in this set, then this energy, which is like the kinetic energy, reduces a little bit because I don't have the potential energy here to worry about. Yeah. So that's exactly what we prove. We prove that there is universal constants so that in that small ball, I lift my function up by this universally but small amount theta. And then this kinetic energy is less than the minimum energy minus, so the difference between the kinetic energy for this lifted function, say, minus the minimum value is less than a negative number times delta to the n minus 2s. So we can reduce the energy by lifting a little bit nearby. And then we prove a covering limit and we iterate this process. So I do this, I find a finite sequence of balls from 1 to some number n, depending on delta, where that number behaves like delta to the 1 minus n, so that in each of those balls, I lift by the same amount theta, and the corresponding energy, kinetic energy here, is less than that the minimizer minus universal constant, here again, delta to the n minus 2s times the number of balls. So we're able to show this. Now, using this drop in kinetic energy and the fact that this excuse me excuse me we're able to now control the difference in energy of the actual F epsilon 1 energy of my function minus the minimum value. So this was the M1 here. I have the kinetic energy, which is scaled by 1 because I'm in the case S less than a half. And then I have the potential energy here, which has the 1 over epsilon to the 2s. So I showed this difference is less than a negative number with this part having to do with delta. The potential energy, when V delta is equal to the original function, the minimizer U bar, it's equal to plus or minus 1. So the only pieces that this potential energy sees is where I've lifted my function a little bit. And so that's why we're looking only in these balls. And so what do you get there? You get, well, some constant depending on a measure of the unit ball and the potential and this theta. And then you have the number of balls times delta to the n coming from the measure again. And pull out this universal factor and delta to the n minus 1. And the point is that we have control here because of this epsilon as well. So this behaves like 1 because n delta behaves like delta to the 1 minus n. That's the number of balls we get in our covering argument. So then you just do calculus. You find where this number is minimized. Well, it's by choosing this particular delta, which is some number times epsilon. And when you plug that in, you get a negative value. So you get C naught epsilon to the 1 minus 2s. And again, this behaves like 1. And then if you divide by epsilon to the mu, you have a minus mu there. And you can see that this diverges when mu is bigger than 1 minus 2s as epsilon goes to 0. So that's the idea, this lifting is the idea behind why you have, or how we were able to prove that you don't have these higher order asymptotics up to or past a certain threshold. Now, for the rest of the talk, I want to focus on the localizing regime or the genuinely localizing regime to be consistent with my terminology. So now we'll consider the case that S is bigger than or equal to a half. And we had to restrict ourselves to 1 dimension. And I can talk about that later, but for the rest of the talk, we're in 1 dimension. S is bigger than a half, so our domain is a bounded interval. And what we were able to prove is with a constraint, a first order asymptotic development. So the big question here was, what is the boundary data? How do you understand what's happening at the boundary? And then hopefully eventually we'll be able to talk about what happens in the second order, but we haven't gotten that far at this point. So we assume that G in absolute value is strictly less than 1 on the boundary. And we prove, as I said, a first order asymptotic expansion on the sense of gamma convergence in, I said, this constrained class, which I will mention in a little bit because once I give a little bit more context, it will make more sense. We already talked about the 0th order term, which is 0 when S equals a half and the potential energy when S is bigger than a half, which I can write in this way. And then we proved that the first order term is the perimeter functional plus a penalization term on the boundary. So you have the perimeter in the interior, say. So again, here U is equal to 1 and E and minus 1, excuse me, in the complement. And so that's recovering Savin and Baldinocci's result in the local case. Our contribution is that we're able to say something about what happens on the boundary. So here, this is an integral over the boundary of omega with respect to the 0-dimensional Hausdorff measure. So we're in 1D, so this is just evaluation at the endpoints, but just to make it a little easier to write down on the slides. So this function depends on G at X for X in the boundary. So which is well defined because G is a Lipschitz function and it's fixed. But the point I want to make here is I said earlier we have localizing to a when the gamma convergence, you get the local classical perimeter functional, and I said you're going to get localizing behavior with the boundary conditions as well. So here we don't see or we don't need information about the values of G in the complement of omega just at the boundary. Not the full complement, just what happens at the boundary. So you see this localization with the boundary data as well. It also depends on the values of U at X. And this, I'm not writing it, so I'll just say it out loud. I'm in 1D. This is defined in the trace sense. And the perimeter is finite in this case. Otherwise, the energy blows up anyways. So when I write U of X for X in the boundary, it's defined in the trace sense coming from the interior. All right. And because we have this asymptotic expansion, we have an expansion for minimizers as well. Excuse me. Okay, so I haven't said what this function is, so that's the kind of the last part I want to address. What is this, what I call the penalization function on the boundary? Well, to understand it, we want to think about what's done in the interior. In the interior, to prove the gamma convergence, you use these heteroclinic connections that in an energetically appropriate way connect -1 to 1. So they give you a way of connecting the two phases in the interior. We want to do something similar at the boundary. So here's again, a hand-drawn sketch of just potentially what could happen. I have my domain omega, and what I'm going to be doing is assuming that 0 is my right endpoint of my domain omega, and I'm going to mainly be focusing on what happens nearby that endpoint. Outside of there, there's a lot of patching that happens, but just to give you an idea, we'll focus near that right endpoint, which is going to be 0. We'll assume, again, just to normalize the problem, that U at 0 is -1, so defined in the trace sense. So you're jumping from -1 up to your boundary data, which I'm going to call gamma. So G at 0 at that boundary point, I'm going to call gamma. Here I drew it above 0. It could be down here, but this is just a sketch. And as I say, I want to somehow energetically make the jump from -1 up to gamma. And as a note, this doesn't follow from what's done in the interior from -1 to 1. We tried to make it work. It didn't, partially because of this boundary part here, oops, not being one of the wells of your potential, plus or -1. And yeah, we couldn't get that to work. I can say a little bit more about that later. I think I say that. So how do we handle this? Well, the idea is we'll fix gamma in -1, 1 because we're assuming G is strictly, our boundary data G is strictly less than 1 in absolute value. So gamma is between -1 and 1. And we'll consider the class of functions that are gamma in the right half space. So when x is positive, constantly equal to gamma, and less than or equal to gamma everywhere. So this is an idealistic picture. Of course, there could be oscillations, isn't necessarily approaching -1 as x goes to -infinity, but that's what we'd like to achieve. And then we take the closure of this space with respect to the HS seminorm to get our function class. Oops. Okay. Now, what energy? I said we need to do energetically appropriate way of making this connection. So what energy do we use? Well, we use an energy in the left half space. So when x is less than 0. So in this class of functions, which I'm calling x gamma here, and in the case s strictly bigger than a half, I look at my kinetic energy where my domain is r minus. So the complement of r minus is r plus. So that's why we neglect what happens when both particles x and y are in the right half space. And then we have our potential energy again in the left half space. For s equals a half, we have to be a bit more careful because this energy doesn't converge in the case s equals a half. So we have to renormalize. So what we do is for the context of our problem, we look at an energy where instead of up here, I said you can think about your domain as being r minus. Instead, we think about our domain as being an interval minus r0. So it's like a left-sided interval where the right endpoint is always fixed at 0 because in r plus, my function is constantly equal to gamma. So now here I neglect points in the complement of that where both particles come from the complement of that interval. This goes to infinity. Like I said that up here in the case s equals a half, it diverges because down here this goes to infinity as r goes to infinity like natural log of r. So that's why here we divide by natural log of r to renormalize and send r to infinity. And this is consistent with the scaling that Palatucci, Savin, and Valinocci did when they did heteroclinic connections in the interior. And so this is the energy. We look at functions in this class, x gamma. We look at minimizers, and we use this energy to make the connection from -1 to gamma. And so before I say anything about the existence uniqueness, which is an important part if you're going to use those functions, you should know they exist. But let's just say for a moment that we have a minimizer. Not only do we have a minimizer of this energy G, which I don't think I said it out loud, that is the this energy in the half space that I defined. And suppose that that minimizer goes to -1 as x goes to -infinity. So it has this it looks like this idealized picture, which we can prove it looks like this. Then again, I said we're gonna look just near the boundary. Away from it, we can handle. So 0 is in the boundary, and say -1, 0 is in omega. Okay, so for the gamma convergence, I need a recovery sequence. So I need my function to converge to -1 here, and G needs to be G and the complement. So in the ball B1, I'm going to say my recovery sequence, it has to have the boundary conditions. So it's G of X and 0, 1. I'm going to take this minimizer up here and rescale by X over epsilon. And so similar to what's done in the interior. Because then looking at this idealized picture, or looking at this picture, as epsilon goes to 0, this jump becomes sharper and sharper and sharper, so that in the limit, you go to -1 and gamma. Or -1 up to gamma, and then of course G in the complement. So this is what we want to use to make the connections at the boundary. So if we do that, if we look at our energy near the boundary, so I'm going to ignore some of the long-range interactions and other interactions in the interior and say, let's just look at when X and Y are both in -1, 0, so in the interior, but near the boundary, and these cross terms. So when X is in -1, 0 and Y is in 0, 1. So these are, again, what's happening near the boundary and the potential energy in the same area. Then I use my definition of my recovery sequence U epsilon. So in the interior, U epsilon is V at X over epsilon. So when I rescale, I just have V of X minus V of Y. My integration is now -1 over epsilon to 0, and then -1 over epsilon to 0. And then from the change of variables and with the kernel down here, I have, instead of A epsilon over epsilon, I have A epsilon over epsilon to the 2s. For the cross terms, very similar, except when I'm in the complement of omega, I have U epsilon is equal to G, so I have G of epsilon Y. And then the potential energy rescales, and I just have B epsilon. Now, if you look at this and think about what happens when epsilon goes to 0, well, at least morally speaking, as epsilon goes to 0, G of epsilon Y looks like G of 0, which is gamma. That's not precise, we have to be careful, but we can show that any other terms are lower order terms by making the G of 0 appear there, which is gamma. And then if we look at the coefficients here, these reduce to exactly the coefficients that we need so that when epsilon goes to 0, this is like sending R to infinity. So R is like 1 over epsilon in our rescaled energy G that we had. So in the case S bigger than a half, this is just 1. The A epsilon over epsilon to the 2s is just 1, and B epsilon is just 1. In the case S equals a half, I have 1 over absolute value of natural log epsilon for both of them. So what happens then when epsilon goes to 0, you get that this is behaving, or it is the energy in the half space for my minimizer V. And so that is exactly what we see at the boundary in our asymptotic development. That penalization function is exactly the energy for the function that connects -1 to gamma. And if you were connecting +1 to gamma instead, you can think about just flipping all the pictures and you have an analogous argument. So I think I'm probably supposed to end now. So the last thing I'll say, if you'll allow me just one extra minute, we did prove existence and uniqueness of global minimizers for this connection connecting -1 to gamma. So that's what this is saying. There exists a unique global minimizer in our class. Moreover, we prove it has global regularity CS, and in the left half space, improved local Hölder regularity. We also prove it is strictly increasing, and as x goes to -infinity, v of x goes to -1. So that idealized picture I drew is exactly what the minimizer satisfies. It has the boundary conditions equaling to gamma in the right half space, and it solves this fractional PDE in the left half space, which, if you're familiar with is non-local energies and operators, it's exactly what you expect. A couple small notes really quick is that in the case gamma is between -1 and 0, you can prove that minimizers satisfy this limiting condition that they approach -1 as x goes to minus infinity without the constraint that v is less than or equal to gamma. And we need that limit to make the connection from -1 to gamma. But without that constraint, minimizers instead want to satisfy that, they will satisfy, we haven't proved it, but I can confidently say they satisfy that as x goes to minus infinity, they go to +1. So if you start above 0, energetically you don't want to go down, you want to go to the closer well of your potential, the closer phase, I should say. So this is the constraint that we have in our asymptotic development, that near the boundary, we don't allow our functions to cross 0. So if the boundary data is above 0, then inside, in the interior, our function is also above 0. So we're working on removing that constraint. We would really like to do it, and we have some ideas, but that's a work in progress. Gamma equals 1, -1 is trivial in this case, and gamma equals +1 is unclear on how to do that in the gamma convergence. I think I'm at time, so I had a couple of slides about how we prove existence, and the only thing I'll say is the case s equals 1/2 was tricky because of the rescaling. So what we did is we used the fact that we knew existence and properties of uniqueness, etc., of minimizers for the case s bigger than 1/2, and we were able to send s to 1/2 to construct global minimizers in that case, which was a new approach for these heteroclitic connections. And so I think I will stop there, and thank you for your attention and for listening.
Hi, Mary. Thank you very much for the beautiful talk. I kind of have to run, but before I run, can I ask you a quick question, and then I leave the other questions to the other. You have this as you prove that there is no asymptotic estimates for in the case s than 1/2 up to, I think it was 1 minus 2s or something like that. So there is no fractional expansion up to.
But in the non-local case,
The no local case.
yes. Yeah, so we didn't prove there's no higher order asymptotic expansion because we proved from some higher order on there's no expansion, but there's this like kind of
There is a gap, right?
there's a gap, and we don't know what
Yeah, I
happens.
was wondering if you expect something in that gap, or you don't know.
We we've talked about it. We haven't explored it super deeply yet. It's not entirely obvious what it would be. I can't confidently say it, but I kind of wonder. I could just say I wonder if there's a in that at that threshold, there's like a non-local curvature term. That's what I would expect, but I have no mathematical reason to say that. It's just I don't know. We don't know what happens. Yeah. It's a good question. It's an interesting problem, but we don't know.
Okay. Thank you very much. Sorry, I have to leave earlier, so I don't know
No
if.
worries.
Yeah, I can be in charge of the.
Okay, thank you, Hank. Thank you. Sorry about that. Thank you, Mary. Bye.
Okay, see you, Stefania. So, are there other questions for Mary? Okay. Ovidio, you have some questions?
Yeah, let me ask some questions. So you get this second boundary term that connects the boundary data G to U. I didn't understand. Do you require G to be bigger than 0 or less than 0? Like, because I was a little bit confused about you when you find this heterotonic, like you connect -1 to gamma, but you want gamma to be less than 0, or
Yeah, so what we're only able to do, so we can prove existence of these heteroclitic connections with the constraint that that what you're connecting is you're connecting either +1 to gamma when gamma is above 0 or -1 to gamma when gamma is below 0. So that's what we're able to prove, and we don't know how to do it when you want to, for the gamma convergence, when you want to connect -1 to say a half, anything above 0. We don't know how to build that connection.
Yeah, like if G would oscillate like a sine of, I don't know, 100 theta around the circle.
Yeah. Yeah, we don't know. We just don't know how to build that. And so in our gamma convergence, that's why we have this extra constraint that we only look in the class of functions that you have your fixed boundary data, say all of it's above 0 or something, and then you have some ring around the boundary where in the interior we only consider functions that are +1. Yeah, so we'd really want to remove that constraint, but we don't know how.
Okay. Okay. Thanks for the clarification. Okay.
Thank you.
Thank you. So I just have let me see. I just have a very quick questions, more speculative, because you said you want to also find the next order term. So what do you expect from there?
Well, if I look at in the interior, in the classical case, there's this, as I said, this result of Leone and Murray, and they have like a curvature term. So for S bigger than or equal to a half, I would hypothesize that you get a similar term, but I haven't done any computations to check that. So I'm not positive. And yeah, it's an interesting question, but it's all pretty technical, so we're not sure how to do it yet.
Thank you. Just following up on what you said, nothing too deep. Okay, thank you. Are there other questions or comments from Mary? Okay, if not, then thank you very much for a great talk.
Thank you. Thank you, everyone.
Thank you. Thanks a lot. Yeah.
All right.
I
Thank
know,
you.
yeah, maybe